something about the relation between simulation result and its influence, relations between the simulation result and performance of the ship. In this case, the tanker model, the name of the tanker is SR221. It is going in oblique wave. So the pressure field or surface elevation is modified by the wave influence. Although you can see the pattern of Kelvin wave, but it is not significant. In this case, wave elevation, acceleration provided by wave is more significant. These two are, this is the time history of total drag. It is X component of the integrated force. Integrated force on normal stress, it is pressure, and tangential stress, it is provided by viscous effect. So what I'd like to show you is the difference of maximum drag and minimum drag. In the maximum drag, it is similar to this position. The wave, the peak of the wave is near the bow, and it will increase the pressure on the surface. Actually, the still water line is around here, but because of the wave elevation, it get additional wetted surface over this line. So naturally, it will increase the drag of the hull. In the different time sequence, when bow is lower peak of the wave, naturally it will reduce the wetted surface. Wetted surface is always pushed by a ambient water. So the deformation, lower shift of wetted surface cause the decrease of total drag. One important thing is if you look this time history closely, in some cases, this is zero line. So in this point, drag is positive, but in this point, the total drag is negative. It indicates wave push the ship in forward direction. So we are usually discussing the performance of calm water condition because this kind of situation is very difficult to obtain in towing tank. But such a performance in calm water condition is almost disappear in the wave condition because the ship influences acceleration. So the average drag is only this level. You can see the average drag is in comparison to average drag. The influence of wave is very significant.
In the case of the total drag negative, this is the effect of thrust.
Yes, in that point, the wave accelerates the ship. Wave accelerates the ship. So it seems to me that the averaged influence of wave might be zero, but it is not true because slightly this increase of drag is larger than the obtaining thrust. If you can, I guess this is difficult to explain now. The present conclusion is calm water condition is important, at least in a level it is important to optimize the ship. But in the calm water performance does not show the condition of the operation. It is totally different. This is the point. Okay. So this is an example of mesh-based free surface treatment. We are using in this treatment we are using computational mesh and marker density. But recently there are another famous method. It is called CIP method. Actually, it is not not the method for free surface simulation, but many researchers say it is free surface treatment. So there is a misunderstanding in researchers. But I'd like to introduce this one because it is now famous. But in my opinion, the capability of this method is limited if we consider the application of ship hydrodynamics. The CIP method, it is CIP is the name CIP comes from the constraint interpolation profile method. It is proposed by Yabe, he is Japanese, in 2001. As I said, this is not the free surface treatment scheme. Actually, it is a kind of convection scheme. The basics of the CIP method is interpolation in the sparsely located computational grids. This figure illustrates the usual treatment of convection and numerical dissipation. This solid line indicates the present profile, And in natural, if we consider the convection accurately, this line will be move with the velocity field. So next, if the present line is like this, the line in the next step will be like this. But we cannot recognize this part because mesh resolution is limited. We know only the value of this point and this point. At present, it is still 0. We got the increase of the physical value at this point. So although ideal profile is like this, we can only know these points. So this is illustrated like this. We have to reconstruct the profile from this limited information. Naturally, the process is connecting these lines like this. So this is ideal convection, but we can get only this one. The difference is if it is treated very ideally, we should have this part, but it is disappeared. It is a result of this is one understanding of diffusion features, diffusive feature of convection scheme. Then the proposal by Yabe is to avoid this this treatment. We have to use the gradient, information of gradient with the usual information of distribution. His proposal is to use distribution of these physical values, and also use gradient information of these values. At this point, gradient is gradient slope of the value is 0, and in this point, we can consider the gradient is in this direction, and so if we know the gradient of this point, we will not directly connect to this line. If we know the gradient of this point, we will use this curve. So it indicates also in this point gradient is still 0. So if we know the gradient of this point, this point, this point, we will connect not in the straight line. The connection will be like this. It is much better than this simple treatment. So the idea is gradient is also moves with flow speed. Gradient information is also transported by the flow field. So this, after, as I said, the basics of this one is interpolation. after after the calculation of the movement of gradient and distribution of physical quantity, they will reconstruct the profile again. The reconstruction is usually a cubic interpolation. So the name comes from they changed its name. The last name contains cubic, but naturally the method is not restricted to cubic interpolation. So the present name is constrained interpolation. So why it is used in free surface problems, and also why many researchers have misunderstanding on the method is it is very suitable for free surface tracking procedures. In the CIP method, we can consider this is, we can assume this profile is marker density profile or VOA function or level set function. This treatment assures the preservation of this shape in the convection treatment. So this is marker. If this is marker density, this level is for raw water, and this level is raw air. Usually, if we are using simpler treatment, the convected value will be like this. So the thickness of the free surface is increased. So as I said in the last class, it will cause instability in some cases. But if the treatment is described as semi-Lagrangian treatment. Lagrangian is to observe the direct motion of the fluid particles instead of considering the flow field, considering field function. First, I will show you some animation of the CIP method. This is, it shows the green water problems of tanker ship, container carrier. In CIP method, the green water on the forward deck is reproduced, and the resultant force is very similar to the experimental result. So it seems to me, it seems to good, but it has some problems in other applications. I guess the researchers in CIP method will not agree with me, but the point is since this requires interpolation and interpolation and propagation of gradient, the process of convection is procedure of convection treatment is somewhat complicated. So this is very good in regular mesh formation. If mesh is always rectangular and almost uniform spacing, the treatment, this treatment result in good solution. But in the curved linear space, like around the hull surface, the mesh is not equal spacing and it is not rectangular shape. So interpolation of values will be more difficult. This is one more explanation of the CIP method. This is original shape of convection. This is a basic formation of convection, equation of convection. The value F is experience convection caused by a ambient flow velocity U. So U times dF dx, this will cause the, this is the convection term of gradient formation. The basis of CIP is provided by time by generating derivatives of this equation. In this case, df when you make a derivative of x, df dt is now we will consider the partial derivative of x, so it will lead to this one, and we name the slope, it is gradient of f, as gx. So this is a gradient. So if we make derivative of x, it will lead to round d, g round g around t. And also in this part, this will lead to the first term is the derivation of x and plus gradient of u times df dx. But in this case, df dx is equal to g. So the result is this equation. So we can consider this part as the transport equation of gradient, or transport equation of slope. And right-hand side is additional term. You can consider this one is the source term of gradient. Gradient is increased. Its rate is proportional to this one. Slope times anyway, this will transport the slope of the physical value is transported based on this equation, and this part will be added for the treatment. So the treatment is like this, with the last profile is propagated with the value distribution and also the distribution of slope. Then it will reconstruct the profile based on some interpolation. It might be cubic function or other higher order spline method. The one problem of this treatment is for the applicability of complex mesh geometry. The other thing is the requirement of mass conservation or any conservation law, because this considers only the propagation of a profile. It does not give. It will not give the assurance of conservation. So this is similar to finite difference method. So it does not have conservation features of finite volume method. So I will show you the movie again. Why they are although I said it is difficult to apply CIP method in complicated geometry, but this geometry seems to be very complicated. But this is provided by another technique. in this treatment, mesh is always rectangular, and it is not moving. The motion is provided by another particles. The surface of the ship is defined by particles. It will move in digit formation. So I guess this treatment is similar to the free surface tracking. In this case, they are using body surface tracking technique, but the motion of the body surface is precisely estimated by solving the equation of motion. So, although this shows very sharp edges of the ship image, but the image is provided by only superposing the the geometry of the ship in the visualization. So in the actual condition is they are using the simulation of group of points. It represents the shape of the ship. So this is very powerful if you are interested in the application of ocean structures or other things. Even if the geometry of the structure is complicated, this treatment is capable of handle the complexity. But I'm not interested in this one because my field is different from theirs. My interest is on the performance of the vessel. It includes total drag of the ship. For obtaining drag of the ship, this treatment has one disadvantage because it does not provide higher resolution in the boundary layer. In this case, resolution is all the same in entire computational domain. But as I showed you, we need higher resolution around the ship because near the body surface of the ship, it has a very thin boundary layer, and the variation of velocity is very rapid in very thin structures. So if you are interested in green water road or other non-linear wave related phenomena, you can consider this CIP approach. But if it is for the problem of performance, you have to think another choice. Anyway, CIP is very, very powerful in complicated free surface problems. One more example is This is this shows milk crown simulation. This is based on CIP method. This is a result of the simulation, not the experiment. The mesh size is 200 times 200 times 100. So it is 4 million meshes.
Is this simulation?
Simulation. So you cannot see the computational mesh, but I guess it is on the I guess along this level it is covered by the regular mesh 200 times 200 times 100, and CIP method is used to capture the position of the free surface. And this visualization is very impressive. They are using ray tracing technique. Ray tracing is to calculate the path of any light. So it will generate very realistic view of transparent objects like this. So I guess it requires significant CPU time, and also they are using another process, another post-processing for generating this view. Because ray tracing is sometimes very time consuming, because all dot, all pixel should be calculated. For one pixel, you have to calculate the ray path of light, and you have to determine, you have to calculate. It looks how much intensity of light, and what is the color of this point. They are calculated in the ray tracing. Also, in this case, they are calculating free surface surface tension. If we do not consider surface tension, the shape is very different. This is another solution. In this case, they are not using ray tracing. It is very realistic and impressive, because it keeps with the features of CIP method. Free surface front is kept. The sharpness of the free surface is kept very small. It keeps the sharpness of the free surface. This is experiment. This droplet is very small, so the shape is provided by the significant free surface tension in this case. This one is water droplet or oil drop. I think similar toy, jelly-like toy is exist. It is jelly-like a ball, but the material is jelly, so you can throw it on wall. It will almost splash again, but it will recover its shape. But in the toy, the recovery is provided by the shell of the ball. But in this case, recovery force is surface tension. I think I have to explain the treatment of surface tension because I omitted the explanation. If you are using marker density method or other values to capture the free surface position, the contour line of the free surface is like this. The free surface position is the result of drawing ISO value surface in the distribution of marker values. So in this side, we can assume this side is water and this side is air. To calculate the free surface tension, free surface tension is like this. If there is curvature, the tension of the surface provides a push in this direction. So it causes force to the towards the inside of the fluid drop. So it provides covering of the water mass, and the result is these sphere-like shape of drop. So to calculate the free surface tension effect, gradient rho m, gradient of the marker density, it provides the normal direction of the free surface. And its Laplacian provides the information of curvature, how the free surface shape is curved, how small its curvature radius is. It is provided by the Laplacian form. So after you get the curve, the resultant surface tension is given by the coefficient kappa and calculated curvature radius. It will affect in this direction. So the final form of the free surface tension is similar to pressure, but it works only on the free surface. If it is treated properly, the result, we can get this kind of result. So CIP is actually CIP is only the treatment of convection term, but if it is used with the free surface capturing method, like marker density function or VOF or level set function, it will give very powerful solution of free surface problems. But as I said, this is very impressive, but the mesh is only in regular form. It is the mesh is very simple, regular rectangular mesh. So it is not directly applicable to the performance prediction of seagoing vessel. But this might be very applicable to sloshing problems if the tank shape of the tank is very simple. I'm sorry, I have prepared some more slides, but it is not come here yet. Okay, then I will give you other information for the lead driving cavity flow. You have finished, most of you have finished the treatment of convection and diffusion. So remaining task is to provide pressure solution. This is sample of pressure solution. You have already calculated convection and diffusion term and assume it is stored in this array, du dt. So you can imagine this is the acceleration caused by a diffusion term and convection term. So first thing is to calculate predictor velocity. In this pressure solution, we will use predictor velocity like previous velocity field plus acceleration. This is predictor. Then we calculate required pressure distribution to satisfy the mass conservation law, divergence free field. Then we get collector. It is a next step. It is a velocity field of the next step. So we get predictor velocity field, then calculate pressure, then get the next velocity field. It is predictor velocity field plus pressure gradient. So the present source code covers this part. So this one is to calculate predictor velocity, and next we calculate divergence of the predictor velocity. What we have to calculate is like this. We require this condition. Divergence of the next velocity field should be equal to 0. So it indicates divergence of predictor velocity minus divergence of pressure gradient times time increment is equal to 0. So we have to calculate pressure distribution which satisfies this condition. For this purpose, first thing is this one. It is divergence. It is said divergence U in this programming code. The process is to get the area vector of the control volume. We consider primary control volume. It is this vertex is xij, and this one, I'm sorry, the present problem is two-dimensional, so the condition is xij and xi plus 1, j plus 1. This is the present control volume. To get to the divergence, the process is very simple. We have to get mass flux of these four phases using the predictor velocity. S1 is the size. S1 is the size of this edge. In general condition, it should be a vector value, but it is since this is in simplified regular condition, we set only the x component of S1 vector. It is the size of this size of this edge, and also S2 is it should be vector in the general form, but at present we calculate only the length of this edge. So volume of this control volume is the product of S1 and S2. Then divergence of this control volume is U1 I plus 1 times S1. It is the first one is escaping flux from this surface, and minus U1 Ij times S1. It is for this surface, and U2 J plus 1 times S2. And last one is U2 Ij times S2. And the sign is minus. So this four component provides the divergence, total divergence of the control volume, and it should be divided by the size of control volume. So and in this point you get the information of divergence. It does not satisfy incompressible condition because it is only the predictor velocity. It does not. It is only provided by diffusion term and convection term. So we have to correct the error of divergence. The correction procedure is just in this screen. Is it complicated? But the essence is very simple. First one is calculate the divergence of pressure gradient. The predictor velocity might not satisfy the incompressible condition, so it might be like this. In some direction, it has compression or depression. So we have to cancel this compression or depression effect provided by a predictor velocity by adding pressure gradient. pressure gradient times delta T. You can understand this one as the velocity change caused by pressure distribution. So we can calculate the divergence of velocity change of this one. And if it cancels the already evaluated divergence of predicted velocity, it will satisfy the total divergence-free condition. For calculating this one, first thing is to get the pressure gradient. It will increase the this is pressure point, this is U point. Calculate the increase of velocity at this point. This is provided by this secondary control volume. This velocity is pushed by the pressure point next to pressure point. So Pi minus 1, this will push the velocity point by the area of S1. Since it is in regular mesh, size of S1 is always the same. So I omit the precise calculation of S1. S1 and S2 is like this, and we assume it is uniform in the present local consideration. So this will Pi minus 1 push the present U1 point, and Pij, this will repel this motion. So effect of the pressure distribution at this point is pushed by this from this side and also pushed by this side. The total balance is the acceleration of Uij at this point. So push by I minus 1 pressure and push by I pressure, and since direction is changed, it has minus sign. And it will occur in a time increment delta t, and it should be divided by the volume of secondary control volume. Also, we have to consider next one. Next one is for this point. In this point, pressure, this point is pushed by Pij and repelled by Pi plus 1j. It is here. It is on this volume. And also in this volume, and also in this volume. This is U1, left side U1, right side U1, and lower side B component, and upper side B component. So this is the divergence of pressure gradient. So next step is determine the required pressure change to provide this condition locally. It is written in this code as a memo. It says divergence of predictor velocity and divergence of pressure. If the pressure should be changed from P to P plus delta P, we have to calculate dP. And we can, the approximation of this one is, this one should be calculated in approximation. It is, this part is original divergence plus some coefficients times delta P. If we get this one, we can calculate dP as like this. And this Cij is provided from this one, this form of divergence P. The Cij is, this is the inference of the inference of Pij on the divergence. So we can calculate it like this. Delete this part. What we need is the change of divergence P if we change only Pij, while other pressure values are not changed. Now I deleted other terms of divergence P, and required value is when Pij is changed by unit number. So we replace this one as 1. Minus times minus, so it is plus. This one is also plus. Do you understand? Then the result is this one. What I did is to I calculated divergence P numerically, and to get the exact coefficients of the influence of Pij in this form, we modified the programming code directly and obtained this one. So after that, we can calculate delta P. It will this will cancel the divergence of predictor velocity by the new divergence of the pressure gradient. But it is on the assumption that Uij is changed, pressure Ij is changed, but other pressures are not changed. This this value is on the assumption. So the result does not go directly to divergence-free velocity field. So we need other mechanism of acceleration. If the resultant dp is positive, we can expect dp of surrounding pressure values are also positive. So only dp, the direct result of dp is not sufficient to satisfy the next divergence-free condition. So we will use acceleration coefficient. Omega is 1.2. It will magnify the change of pressure to get faster solution of pressure Poisson equation. I guess it is too much for you. Okay. Please consider this again for the next treatment of the pressure solution. Okay. Thank you very much.